Welcome to 7.3, the law of cosines. We are going to start with a derivation of the law of cosines and then get into some examples. So looking at this triangle, what you need to know is that you have to, in order to prove this law of cosines, you need to put one of your angles at the origin. So we have here ABC, where B is at the origin, C is on the x-axis, and in this case we have A in quadrant 2. A could also be in quadrant 1 if this were an acute triangle. So if we look, since B is in standard position, we could calculate the cosine of B, and that's just going to be x over r. But in this situation, r is actually C. So looking at this triangle right here, we can see x over r, but our r value is C. Sine is y over r, but r is C. So sine of B equals y over C. If we wanted to solve for x and y, for the top, we multiply both sides by C to get x equals C cosine of B. And in the bottom equation, we get y equals C sine of B. Since the coordinates of A are x and y, we could write those as C cosine of B and C sine of B. Now for point C, notice our x value is A and the y value is 0. So the coordinates of C are just A, 0. Now, in order to find an expression for the distance of side B, we could use the distance formula. I'm going to use the A as my x2, y2, and C as my x1, y1. So we get C cosine of B minus A. All of that will be squared. And for the y minus y, we get C sine of B minus 0. Now we will go ahead and square out each of these terms. On the left, we multiply it out to get a perfect square trinomial. On the right, this just ends up being C squared and sine squared of B. So we get the square root of C squared cosine squared B minus 2AC cosine of B plus A squared plus C squared sine squared of B. You might notice that there are two terms with a C squared in it. So let's put those together. We will reorder them so that the C squareds are adjacent. So we get the square root of C squared sine squared B plus C squared cosine squared B minus 2AC cosine B plus A squared. Now let's factor out that C squared just from these first two terms. Look at that. We have C squared times the quantity sine squared B plus cosine squared B. And then we'll bring down the rest. But notice sine squared B plus cosine squared B is just 1. So we just get the square root of C squared minus 2AC cosine of B plus A squared. Remember, this whole thing gives us the length of B. So in order to get it into the form of the law of cosines, we will actually go ahead and square both sides. So we get B squared equals C squared minus 2AC cosine of B plus A squared, since the square and the square root cancel. However, the way we will order it is we have the B squared equals A squared plus C squared minus 2AC cosine of B. So the A squared and the C squared are together in the front. So this is one version of the law of cosines, but notice that we put angle B at the origin, but we could have put any of the angles at the origin. So we also have A squared equals the other two, which is B squared plus C squared, minus 2. The two numbers here that go on the right-hand side will stay here, so it will be 2BC cosine of this angle here. So it's going to be cosine of A. Similarly, we get C squared equals A squared plus B squared minus 2AB cosine of C. Notice the two numbers that are being squared and added together are always the same two that are being multiplied by the 2 and the cosine. And the side that's isolated will always match the angle inside the cosine. Example 1. A surveyor wishes to find the distance between two inaccessible points A and B on opposite sides of a lake. While standing at point C, she finds that side B equals 62.5 meters, side A equals 79.4 meters, and angle ACB measures 82 degrees in 20 minutes. Find the distance C. So this is a perfect example why we don't always just measure things directly. So in this case, this is a lake, and this length C was not easily measurable. However, the lengths along the sides of the lake were reasonable to measure, as well as the angle. So this, just by having these more accessible measurements, we will be able to find this third measurement of this triangle. So whenever we are trying to solve a triangle that is not a right triangle, the first thing we want to do is try and apply the law of sines. However, we can see here that we don't have any of the angles and sides that are opposite each other. So there's not enough information to be able to use the law of sines. That's when the law of cosines comes in. And so we have to figure out which version we're going to use. Since we're looking for side C and we have angle C, that's going to be where the C squared is on its own. So that's going to be A squared plus B squared minus 2AB, and the cosine of the whatever side by itself. The angle opposite goes inside the cosine. So now we just go ahead and plug in these numbers. So we get C squared equals 79.4 squared plus 62.5 squared minus 2 times 79.4 times 62.5 times the cosine of 82 plus 20 over 60, converting it into degrees. Plugging this all into the calculator at once carefully gives us C squared is approximately 8,886.5, but with other digits. We will keep that number in the calculator and take the square root of both sides. Normally we would get a plus or minus, but we're talking about a distance here, so we'll take the positive, and we get approximately 94.3. Since this is a distance, we will make sure to include our units, which was meters. So the length across the lake was 94.3 meters. Example 2. Solve the triangle ABC if angle B equals 73.5 degrees, side A equals 28.2 feet, and side C equals 46.7 feet. You might try to use the law of sines. My general rule of thumb is try to use law of sines first, and if that doesn't work, then we resort to the law of cosines. So noticing that we have side A and C and angle B, this will allow us to solve for side B. So we will use the formula B squared equals A squared plus C squared minus 2AC cosine B. Plugging in the numbers, we get B squared equals 28.2 squared plus 46.7 squared minus 2 times 28.2 times 46.7 times the cosine of 73.5 degrees. Plugging this into the calculator, we get B squared is approximately 2,228. Again, leaving this in the calculator, we take the square root of both sides. So B is approximately 47.2, and our units of length are feet. Now that we have all three sides and one angle, and more importantly, we have side B and angle B, or an angle and a side that are opposite each other, now we are able to use the law of sine. This will allow us to solve for either angle A or angle C. I'll go ahead and go with angle A. So sine of A over A equals sine of B over B, since we have both angle B and side B. Plugging in the numbers, we get sine of A over 28.2 equals sine of 73.5 over 47.2. If you want to be extra careful, you will maintain the number for B in the calculator and use the answer key. That will avoid any rounding error. If we multiply both sides by 28.2 or cross multiply and solve, we get 28.2 sine of 73.5 all over 47.2. Sine A is approximately 0.573. Again, we can leave that in the calculator. To find A, we do sine inverse of that answer. And we come up with A is approximately 34.9 degrees. Now, since we know two angles of the triangle, to find the third, we just subtract these two from 180. So C equals 180 minus B minus A, or 180 minus 73.5 minus 34.9, and we get 71.6 degrees. So now we have found all three angles and all three sides of this triangle. Remember the general plan of attack. First, try and use the law of sines. When that doesn't work, use the law of cosines, and then you can switch to the law of sines once you have enough information. I hope you enjoyed this video. See you next time.